Welcome to lecture number 18 for EE206 Circuits 1, Inductors. Now, we've been dealing with capacitors in the past. Capacitors deal with voltage and store energy in an electric field. Inductors, in contrast, deal with current and store energy in a magnetic field. With capacitors, each capacitor adds a differential equation to the circuit. Each inductor also adds a differential equation. So you can basically tell the order of a circuit by just counting how many energy storage elements there are, how many capacitors and inductors there are. Now, in theory, inductors, capacitors are all interchangeable. In practice, if at all possible, you try to use capacitors. The reason being is that inductors are far from ideal. Unlike electric fields, magnetic fields do not have a starting point and an ending point. That means that the magnetic field that goes through the center of the inductor has to go outside the inductor as well. Place the second inductor over here. If the fields overlap, I have crosstalk. You don't have that problem with capacitors. Second problem with inductors, it takes a lot of copper, a lot of windings to produce a sizable inductance. A large amount of wire means a large resistance. So inductors also have a large resistance, unlike capacitors. And third, you almost have to use iron in an inductor. Iron has a relative permeability as much as 1,000 times higher than air. By using iron, that makes inductors very heavy. So with all that, given a choice, I try to avoid using inductors. Sometimes there just isn't a choice. You have to use an inductor. Anytime you're trying to build an electromagnet, you inherently have an inductor. For example, a speaker is an electromagnet. If you look at the cone, when I apply voltage to it, that pushes the cone up and down through an electromagnet. That electromagnet inherently is an inductor. Motors use electromagnets. This is an AC induction motor, for example. This is the stator right here. You see a large amount of copper wire going around an iron core. Wire wound around an iron core is an inductor. Motors are inherently inductors. Transmission lines are inductors. When you have current flowing through a transmission line, that produces magnetic field. The magnetic field has energy. Energy in magnetic field, again, means inductance. To give an idea of how much inductance we're talking about, suppose I take a piece of iron and wrap 100 windings of copper wire around it. Determine the inductance. From electronic tutorials, the inductance is permeability times number of turns squared times area over length. Work that all out. It's a 0.01 or 10 millihenry inductor. So inductance typically isn't very large. The resistance, however, it takes 2 meters of wire to produce that inductor. At 1.38 ohms per meter, you've got 2.77 ohms. So you simply can't avoid resistance with inductors. If I make the windings thicker, I have less resistance, but then it's much heavier, much larger inductor. This shows up with the inductors you can buy from DigiKey. If you want a large inductance, like this one is 1 Henry, it's going to have a large resistance because it has a lot of copper wire in it. If I want low resistance, I'm going to have low inductance. There just isn't that many copper wires in there, not many windings. If I want a small inductor, you get both, low inductance and the high resistance. So inductors have a lot of problems. Second example for calculations. Suppose I have a transmission line. I want to go 1 kilometer of a transmission line that's 1 centimeter diameter at 60 hertz, of course. From Wikipedia, the inductance works out to be 2.3 millihenries per kilometer. Again, that doesn't seem like a lot, but when you have 1,000 kilometers of transmission lines, you've got 2.3 henries. It starts to add up for utility grids. The inductance, along with the capacitance to ground, transmission line to ground is actually a parallel plate capacitor, produces an LC resonant circuit. That's one of the problems you have with transmitting power. You inherently have inductance and capacitance in the transmission lines. For the VI characteristics for an inductor, the basic equations are V is L di dt. The voltage is L times the change in current. Inductors want to keep the current constant. If the current's constant, I have a constant magnetic field, constant amount of energy. If I have energy in the magnetic field and I try to stop the current, the field collapses. The energy has to go somewhere. the collapsing field keeps the current flowing in the same direction. The energy stored in the magnetic field is 1 half Li squared. So what that means is if I have a circuit with inductors in it, each inductor adds one differential equation. And it's a differential equation in terms of current. For example, if I have this circuit and I want to write the differential equation for it, I have, assuming V0 is 10 U of t, I first turned it on. The voltage across the inductor is L di dt. The voltage is V0 minus 50 I1. So substituting, assuming L is 1 Henry, gives you the differential equation in terms of current. If I solve that numerically, like we did before with capacitors, I've got the differential equation for current. I will then integrate over 100 milliseconds, and what you see is that the current builds up just like the voltage on a capacitor built up. The voltage across the inductor starts out large. It initially blocks the whole 10 volts and then drops off down to 0. That's typical with inductors. For an ideal inductor, the voltage at DC is 0. If the voltage isn't changing, there is no voltage drop across it. With inductors, I can also amplify voltages. This is how alternators work. When I put energy in an inductor, apply current to an inductor, they build up energy in the magnetic field. If I try to stop the current from flowing, the energy in the magnetic field has to go somewhere. When the field collapses, it'll generate voltage. The voltage is whatever it takes to find a path to ground. It can't be thousands of volts. That's how the spark plugs in your car work. I first charge up the coil in the alternator, and then I suddenly turn off the current. The path to ground for the collapsing field is through the spark plug. So a 12-volt battery can produce thousands of volts using an inductor or an alternator. To illustrate that, here's the circuit. I'm going to have a variable resistor that's trying to simulate a switch closed, switch open. When the switch is closed, I have 5 ohms, and the 12-volt supply builds up current, builds up energy in the inductor. When the switch opens, I'll switch that to 1,000 ohms. The energy in the magnetic field collapses, and it has to go somewhere. It'll go through this 100 ohm resistor. The differential equation to describe that is the voltage V1 is L di dt. The voltage V1, or this current, is V1 minus V0 over R plus V1 over 100 plus I1 equals 0. Substitute, and I get the differential equation for di1 dt. I can now simulate numerically. I'm going to start out with current at 0 and then switch. Every half second, the resistance switches from 5 ohms to 1,000 ohms to 5 ohms to 1,000 ohms. And here's what happens. When the resistance is 5 ohms, the current builds up. And that's that exponential rise like we saw before. When it's 1,000 ohms, quickly the current goes to 0, or close to 0. At 5 ohms, the current builds up. 1,000 ohms quickly goes to 0. The voltage is L di dt. Here the slope is small, so the voltage is small, negative actually. Now the slope is positive, I have a huge voltage. So here a 12-volt battery is producing 2,000 volts due to turning the inductor on and off. Again, that's how spark plugs work. Using an inductor, I can produce a large amount of voltage. That's lecture number 18 for EE206, Circuits 1. When you have inductance, again, each inductor corresponds to a differential equation. 2 inductors means you have a second order, two first order coupled differential equations.